Okay, here's another very practical and very interesting example of differential equation models. Carbon dating. Now, carbon dating is that we have this C14 special organic element. So this radiocarbon. So this radiocarbon is in the atmosphere and it interact with the atmospheric nitrogen and cosmic rays, and these things will come down to Earth and will incorporate with plants with photosynthesis, what we learned in basic biology, and then animals and plants will acquire this carbon 14. Now, what happens after plants and animals acquire these carbon 14, especially animals eat these plants and then they also get this carbon 14. Now, when a plant or an animal dies, the interaction of carbon 14 with the outside environments all of a sudden stops. So then you have an amount of carbon 14 in the dead animal's body or the dead plant, and it start to decay. Okay, it will stop interacting with the environment. Now, after thousands of years, we get the fossils of animals and these plants, and we can find the amount of carbon 14 left, and that is how we find the age of the fossil. How old is this fossil? Like dinosaurs, we find dinosaur fossils and we analyze the carbon 14 amount left, and we use these differential equation models and find the age of the dinosaur. How long before was it dead or lived? Okay, so that's carbon dating process. Again, it's the same differential equation. dA over dt is equal to Ka. Decay rate is K, and we saw that the solution for differential equation is initial amount times e to the kt. Now, we are specifically interested about C14. Scientists and mathematicians have found that C14, the half-life is 5,730 years. Okay, so we know this for a fact. Now, the other thing is that I would like you to read this note. I picked it up from Wikipedia, and if you like more, you can go to the link and you can read more about this. Okay, it's very interesting. Now, let's go ahead and do a problem to understand the process. A fossilized bone is found to contain 0.2% of its initial amount of carbon 14. Find the age of the fossil. Now, see how less data is given. We don't know the initial amount, and all we need to find is the age. But here the one advantage is we know the half-life. Okay, so we have two constants, right? Two unknowns, initial amount and K. Now, we are not given the initial amount. Probably we are not going to find it before solving the problem, but we can find K, right? Because we know 5,730 is the half-life. Half-life means A naught becomes A naught over 2, half of its unknown initial amount, and the time it takes is 5,730 years. So we can cancel out A naught. See, knowing initial amount doesn't matter, so we get half is equal to e to the 5,730k. Now let's take the natural log of both sides, so natural log e to the 5,730k. Now we can write 5,730k in front of natural log, so natural log half is 5,730k natural log e. Natural log e is 1, so we get our k to be natural log half over 5,730. So this is the constant k. Okay, so we know constant k much better, and we know A naught doesn't matter. Now we need to find the age of the fossil. Now we know 0.2% of the initial amount is left, contained, right? Okay, so we know 0.2% of A naught left, not the decayed, left, A naught e to the kt. We just need to find time, right? Solve for t, because we already know k from here using half-life. So 0.2% means 0.2 A naught divided by 100. Now we know A naught cancel out here. See, it doesn't even matter. So 0.2 divided by 100 is 0.002 e to the kt. Okay, so now let's take the natural log of both sides. So natural log e to the kt, which is kt natural log e. Natural log e is 1. So t is actually, when you divide by k both sides, ln 0.002 divided by k. Now we know k, you can plug this into your calculator and we can find the t, right? So according to my notes, time here is 51 and 374 years. So the bone is this much old, this much years old. Okay, all right, so I would like you to contrast this problem, compare this problem with the previous video's problem, and understand how would you use the half-life or how would you find the half-life. Okay, all right, thank you.